So in the previous session, we have seen that for our dependent sequences, initially we have to develop a statistical model, and that model will be used for the calculation of entropy, right? So today we will discuss how to check the statistical model, or how to write the statistical model of a dependent sequence source or a source with memory, and which are the various representations that we will be using. So, Markov statistical model for information source. Okay. So now if I consider a source, the source can be in any one of the n possible states. So source is assumed to be in n different states, and whenever you consider a source, it can be either in state 1, 2, 3, or it can be in any state up to n. So probability that it is in state 1 is always represented as P1. Probability that source is in state 2 is represented as P2, and so on. Okay. So generally the state of the source is represented with the capital letter S. So S represents the state of the source or a system, and the source changes its state from I to J with a transition probability of Pij. Suppose your source is in state 1 and this is another possible state of source, and assume that this is another possible state of source. So here n value I am taking to be 3. Therefore, it can be in any one of the 3 possible states, either in state 1, state 2, or state 3. And the associated probabilities would be P1, P2, and P3. Now, the source changes its states from I to J. Suppose if it is in state 1, it changes its state from 1 to 2. And what is the probability of changing the state from 1 to 2? It is nothing but the transition probability, that is P12. Probability that the source changes its state from 1 to 2. Similarly, if it changes its state from 1 to 3, then its equivalent probability, or the probability with which it changes its state, is represented as P13. Okay, so the change in state of a source is always represented with the help of transition probability Pij from state I to state J. This transition probability assumed to be constant as source continuously emits the symbols. Whenever the source changes its states, it emits a symbol. So whenever your source is changing its state from 1 to 2 with certain probability of P12, it emits one of the symbol, and that symbol is always represented with small letter S. Okay, so S1 is the symbol emitted by the source when it makes a transition from 1 to 2. Similarly, S2 can be another symbol that can be emitted when the source makes transition from 1 to 3. Similarly, it can make a transition from 2 to 3, or it can make a transition from 3 to 2, or it can make a transition from 3 to 1. Similarly, it can make a transition from 2 to 1. We have to represent the corresponding transition probabilities and the symbols that were emitted whenever a transition will occur. Now, if I assume that the source emits m symbols with certain probabilities, then those symbols are represented with the small letter s. That is symbol S1, symbol S2 up to symbol Sm. And the sequence of random variables are x1, x2 up to xk. That is S1 can be equal to x1. That, for example, if I assume that x1 is the first symbol that was emitted, my x1 is not necessarily s1. Your source can output any symbol from s1 to sm, any one between s1 to sm during the first random interval, and that is represented as x1. Okay. Similarly, during the second random interval, again it can emit any symbol between s1 to sm, and that is represented as x2. So x1 to xk, here you can see that we have not written it as xm because it depends upon the length of a message. It depends upon how many sequence or how many symbols that your source is emitting. Depending upon that length, we have to take so many random variables. Okay. Now if I say that the kth symbol has been emitted by the source, so I am taking that as xk. That is, during the kth random interval, a symbol has been emitted by the source. And as I said, it can be any symbol between S1 to Sm. In general, I am representing that as Sq. Since it is the kth interval I am considering, and due to the fact that it is a dependent sequence, that is, the sequence is emitted by a source with memory, we are very clear that the occurrence of xk depends upon all its previous symbols during the interval x1 to xk minus 1. Therefore, occurrence or emission of a symbol during the kth random interval depends upon all the symbols that were emitted during its previous random time intervals, that is x1, x2, x3 up to xk. That is what we are trying to say here. The probability that the kth symbol emitted is equal to Sq depends upon all its previous symbols x1 to xk minus 1. Okay. So here x1 to xk minus 1 we are using just to say that it is a dependent sequence. And the influence of these x1 to xk minus 1 on xk can be represented by a state of the system which is called as Sk. Okay. So anytime if I write Sk, that says that it is the state of the source at the kth random interval, and it is influenced by all the symbols that were emitted between x1 to xk minus 1. Okay, so Sk is nothing but the state of the system during or at the beginning of kth symbol interval, and it is influenced by x1 to xk minus 1. Therefore, instead of writing this expression, I can simply replace the influence of these random variables with state of the system Sk. Okay. Now, at the beginning of the first symbol interval, we will say that system is in one of the n possible states. That is, either it is in state 1, or it can be in state 2, or it can be in state 3. In general, it can be in state I. And if it has n number of possible states, so it can be in any one of the n possible states. And everywhere you can see here that we are using 1. This one says that we are considering the first symbol interval. So, during the first symbol interval, your source can be in state 1, or during the first symbol interval, your source can be in state 2, or during the first symbol interval, your source can be in state 3, or it can be in state n. Okay. No. So whatever the representations we have studied, just I'll quickly go through those representations. So S1 is S1, S2, S3 here are nothing but the states of the source. So here our source can be in any one of these three states, and you can see the transition here S2 to S1. Obviously I will represent the probability of that transition as P to 1 because it is 2 to 1, and this transition is from 1 to 2, therefore its transition probability is represented as P12. Similarly, there will be associated probabilities for transition from 2 to 3, 3 to 1. Similarly, from 1 to 3 and 3 to 1, there will be some associated probabilities. Okay, and the probability that it is in state 1 is represented as P1, probability that source is in state 2 is represented as P2, and probability that it is in state 3 is represented as P3. Okay, so if I want to say that the source is in state 1 in the first symbol interval, I will represent it like this. System is in state 1 during the first symbol interval. Even during the fourth symbol interval, if it is in state 1, I will represent it somewhat like this. System is in state 1 during the fourth symbol interval. So in general, this circle we will be using to represent the state, and these arrows we will be using in order to represent the transitions. Okay. Graphical representation of discrete stationary Markov source. Okay. So now consider a source. I am just trying to explain you the graphical representation of discrete source. So here the source is either in state 1, or it is in state 2, or it can be in state 3. So there are 3 possible states, and the transition here can be from 1 to 1. So this transition says that if your source is already in state 1, again it can make a transition or come back to the same state with a probability of 1 by 2, and during this transition it will emit symbol A. Similarly, when it is in state 1, it can make a transition to state 2 with a probability of 1 by 4, and during this transition it will emit the symbol C. Or the source which is in state 1 can make a transition to state 3 with a probability of 1 by 4, and during this transition it will emit the symbol V. Similarly, you can see that when it is in state 2, it can come back to its same state with emission of symbol C with a transition probability of 1 by 2. Or it can make a transition from 2 to 1, and P21 is equal to 1 by 4, and the symbol emitted during this transmission would be A. Similarly, you can analyze the remaining part of the graphical representation. Now with the help, this graphical representation can be written in the form of a tree diagram. So this is our tree diagram. So how to write this tree diagram? So for time being, you neglect this part of the tree diagram. Let me concentrate only on this part first. So how to write this part? So initially I will start with this particular state 1. You can start with 2, or you can start with 3 also. So let me consider the state 1. So when it is in state 1, I am going to represent that with the help of state 1. Okay, this is state 1. And in the previous slide you can see that when it is in state 1, either it can make a transition to 1 itself, or it can go to state 2, or it can go to state 3. So there are 3 possibilities of transition: 1 to 1, 1 to 2, and 1 to 3. That is what we are representing here. It can make a transition from 1 to 1, or it can go to state 2, or it can go to state 3. And whenever it is making a transition, you can observe that during the transition 1 to 1, the symbol emitted is A, and the corresponding transition probability is 1 by 2. So symbol emitted is A, and the corresponding transition probability is 1 by 2 during the transition 1 to 1. Similarly, you observe it for 1 to 2. So when I observe it for 1 to 2, you can see that symbol emitted is C, and transition probability is 1 by 4. So symbol emitted is C, and the transition probability is 1 by 4. Similarly, when it makes a transition from 1 to 3, the symbol emitted is B, and transition probability is 1 by 4. Right? So symbol emitted is B, and the transition probability is 1 by 4. So this is one stage tree diagram. So when it makes a transition from 1 to 1, the symbol emitted would be A. When it makes a transition from 1 to 2, the symbol emitted, or the output of the tree diagram, would be C. When it makes a transition from 1 to 3, then the corresponding output of the tree diagram would be B. So now if I say that my source is emitting a message whose length is equal to 1, then I would prefer only this part of my tree diagram, because A is a message of length 1, C is again a message of length 1, and B is also a message of length 1. But if I want to consider a source which emits symbols or messages whose length is equal to 2, then you have to consider one more stage. Okay. So in order to consider one more stage, again you have to consider the continuation of your first stage output. So in the first stage we can see that there are 3 possible states. So initially I will concentrate only on the first state 1. So from 1, again the possibilities are 1 to 1, 1 to 2 and 1 to 3, right? So from state 1 again I will consider 1 to 1, 1 to 2 and 1 to 3. So this is also, you can observe that this is also same thing, from 1 to 1, 1 to 2 and 1 to 3. So you need not to go back to the previous slide. You can see that we are rewriting the same thing. Okay, because here the initial state is 1 and the next state is 1, 2, 3. Again here the initial state is 1 and next states are 1, 2 and 3. Therefore you can copy down the same thing. Now if I consider this particular sequence, okay, my output would be A, that is the output of first stage, and if I consider again transition from 1 to 1, it is A again. So we mean to say that if my source is initially in state 1 and it makes a transition to 1, it will emit A. Again if it makes a transition to 1, again it will emit A. So there are 2 symbols that were emitted and the sequence is A and A. Similarly, if I want to go ahead with 1 to 1 and then 1 to 2, then my sequence would be A, which is the output of first stage, and for this transition 1 to 2 it would be C. So this is AC. Similarly, if I consider 1 to 1 and 1 to 3, it would be AB. Okay, so these are the sequences that were emitted and we can see that their length is equal to 2, that is n value is equal to 2. Similarly, from 2 you have to consider all the possible state transitions. So from 2 you can observe that either it can go to state 1 or it can be in state 2 again, or it can make a transition to state 3. So again the possibilities from state 2 is 1, 2 and 3. So even from 2 I will consider transition to 1, transition to 2 and transition to 3. And along with this transition we have to represent the transition probability and the symbol emitted. So 2 to 1 I can see the transition probability is 1 by 4 and symbol emitted is A. So transition probability is 1 by 4 and symbol emitted is A. Similarly, look into 2 to 2. So when it is 2 to 2, transition probability is 1 by 2 and symbol emitted is C. So 1 by 2 and symbol emitted is C. Similarly, go ahead with 2 to 3 also. Correspondingly, the symbol sequence I will obtain here is for the first stage it is C, and if I consider 2 to 1 transition it would be A. So it is C into A, and this is sequence CC and this would be the sequence C. Okay. Similarly, we can continue that even for state 3. When it is in state 3, it can go to state 1 or to state 2 or it can go to state 3. And note down the corresponding transition probabilities and the symbols emitted. And finally, you can write the sequence also. BA, and here it is BC, and then we have BB. Okay. So these are the sequences, tree diagram for source in state 1. So here we are assuming that it is initially in state 1 and next level can be 1, 2 or 3 and its successive level can be any of these two. But that might not be the case. Initially your source can be in state 2 also, right? It not necessarily be in state 1. Okay, it not necessarily be in state 1. It can be in state 2 also, or it can be in state 3 also, right? So we have to consider all the possibilities. It is in state 1. Next, by considering the initial state to be as state 2, I have to consider the tree diagram. This is for n is equal to 1, and if I go ahead with one more stage, this would be for n is equal to 2. So you can go ahead with a similar way. You will get to know how to write the tree diagram, and at the end of each stage write down the output sequence symbol: 2 to 1, 1 to 1, 2 to 1, and 1 to 2. So it would be AC. Fine. Similarly, 2 to 1 and 1 to 3, it would be AB. Keep on writing the available sequences. Similarly, you have to consider that it can be in state 3 also, and after that again continue the tree diagram by considering message of length 1, that is the first stage, and it can go ahead with n is equal to 2, that is the output of second stage. If you want to go ahead with n is equal to 2, again you have to consider one more stage from here. From 1 it can go to 1 to 3, from 2 it can go to 1 to 3, from 3 it can go to 1, 2 and 3. So that will give you the sequence of symbols for n is equal to 3, that is message length is equal to 3. So this is how we will write the tree diagram. So one important thing in tree diagram here is we have written everywhere the transition probability and the symbols emitted. Along with that, we will require one more information, that is nothing but what is the state probability. What is the probability that source is in state 1? That is nothing but your state probability. If you can see here, P1 of 1 is equal to 1 by 3. Similarly, P2 of 1 is also equal to 1 by 3. Okay. And P3 of 3 is also equal to 1 by 3. That means that probability that during the first symbol interval it is in state 1 is 1 by 3. Possibility that during the first symbol interval it is in state 2 is also 1 by 3. Probability that it is in state 3 during the first symbol interval is equal to 1 by 3. There is a equal chance that your source can be either in state 1 or in state 2, or it can be in state 3. That is the reason why we have considered the initial state 1 here, and in the next slide the initial state as 2, and in the next slide initial state as 3. Suppose my P1 of 1 is equal to 1 by 2. Okay. Similarly, if my P2 of 1 is also 1 by 2, then obviously your P3 of 1 would be 0. Because the total probability, we know that it should always be equal to 1. If they are 1 by 2 and 1 by 2, the total probability is 1, and well, in that case P3 of 1 is 0. So if P3 of 1 is equal to 0, it says that the probability that your source is in state 3 during the first symbol interval is equal to 0, which is very clear that during the first symbol interval your source will not be in state 3. Okay. So if your source is in there are no chances that your source is in state 3 during the first symbol interval, then easily you can skip this slide. Okay, you can easily skip this part, because the probability that the very first state is 3 is equal to 0. Okay, but however, if the probability is non-zero as given here 1 by 3, 1 by 3, 1 by 3, then you have to assume that initial state can be either 1, initial state can be 2, and initial state can be 3, and you have to consider all the possibilities as we did here. Okay, so this is how we will write the tree diagram by considering the statistical model of the source for dependent sequences. Okay, so now once if you are done with the tree diagram, Next thing is how to calculate the probability of occurrence of a particular message. Okay, how to calculate the occurrence of a particular message. For example, if I want to know with what probability the message sequence AA will occur. So if you are interested in finding out with what probability AA has been occurred, refer to all the three tree diagrams, all the possibilities, and find out your transition probability, the probability of sequence AA. Okay, so for that, initially let me complete this sequence. So this is CA, this is CC, and this would be CB, this would be BA, this would be BC, and this will be BB. Okay, similarly if I go ahead with the next slide, here it would be AA, okay, and it would be AC, it would be AB, and here it is CA, CC, CB, BA, right, then BC, and finally B. Right. Now I am interested in knowing what is the probability that the sequence AB will be emitted by the source. Okay. Now let us check all the three tree diagrams and let us find out where AB is present. As we can see, AB is present here in the first slide, right? So it is occurrence of this sequence is only once in the first tree diagram. Again there is a AB here, right? And again there is a AB here also. So AB has the possibility of getting the sequence AB is available when the initial state is 3, when the initial state is 2, and even when the initial state is 1. So that is what we are representing here. When the initial state is 1, we have seen that AB is present. When the initial state is 2, we have seen that it is present AB, or when the initial state is 3, again AB is present. Okay, so only with the initial state 1 AB does not occur. We should check what are the next states also, right? Here you can observe that the initial state is 1, next state is also 1, and third state is 3. So it is 1, 1, 3 for the sequence AB. 1, 1, 3. So state 1 is 1, state 2 is 1, and state 3 is 3. So it is nothing but 1, 1, 3, right? So this is one possibility. Fine. Next possibility. If you consider the initial state as 2, S1 is 2, S2 is 1, and S3 is 3. That is, states 2, 1 and 3 will give us the sequence AB. So remember 2, 1, 3. As you can see, 2, 1, 3. This is another possibility of getting the sequence AB, right? And come to the third state as the initial state. You can see that 3, 1, 3. So transition from 3 to 1, 1 to 3 will give us AB. So remember 3, 1, 3. You can see that 3, 1, 3. This will also give us the sequence AB. So we are considering all the three possibilities of getting the sequence. So I am just rewriting this expression by replacing R with plus. Okay, because I am interested in knowing the overall probability of getting the sequence AB. So I will rewrite the first part as it is 1, 2, 3, state 1, 1, 3. Okay, 1, 1 and 3 plus 2, 1, 3. So state 2, 1, 3 plus state 313. Right? We are rewriting the same expression here. Now let me consider only this part, how to calculate the probability. So to consider this part, okay, probability that S1 is 1, S2 is 1 and S3 is 3. It says that S1 is 1. Initially, that is the first state is 1. And also it says that second state is 1 when its previous state is also 1. So I am writing it like this. Second state is 1 when its previous state is 1. That is the meaning of this one. Okay. When you take third one, you will say that S3 is equal to 3 provided that its second state is 1 and first state is also 1. So S3 is equal to 3 when its first state is 1 and second state is also equal to 1. So why we are writing this split up? Because your S2 can be 1 either with S1 as 1 or S1 as 2 or S1 as 3. That means that your second state can be 1 when your first state will be 1, 2 or 3. But we are specifically interested in the second state equal to 1 when the first state is also equal to 1. That is why we are writing this conditional probability. Okay. Similarly, conditional probability for S3 is equal to 1 when S1 is 1 and S2 is 1. Okay. So this first term can be rewritten something like this. So probability that S1 is equal to 1, we are writing it as it is. Second also we are writing as it is. But the third one we are reducing the expression. We are stating that S3 is equal to 3. I am writing it as it is. S3 is equal to 3. But S11 and S21 is nothing but your second expression, right? So S11 and S21, that I can simply represent as S1 is equal to 1. Okay. So probability that S1 is equal to 1 is nothing but 1 by 3. Okay. Probability that S1 is equal to 1 is 1 by 3. That is, you can see here. Probability that S1 is equal to 1 when during the first symbol interval is equal to 1 by 3. So we are writing that here. Okay. And what is this 1 by 2? It is transition from 1 to 1. Right? Transition from 1 to 1 is nothing but 1 by 2. Okay. And what is this 1 by 4? It is the next transition, that is from 1 to 3. Okay. Next transition from 1 to 3 is nothing but 1 by 4. So we are writing that also. Okay. So this is for sequence AB when your state is in, your source is in state 1. Similarly, this you will obtain for the sequence AB when your source is in state 2. And this you will obtain for the same sequence AB when you assume that your source is in state 3. Let me consider for this one. When you consider state 2, what is the probability of getting the sequence AB? For that I will go to state 2 tree diagram. Okay. So what is the probability of getting AB? The state probability is 1 by 3. Right. So it is 1 by 3 and then follow this link. 1 by 3 state probability multiplied with 1 by 4. This is again multiplied with 1 by 4. So because these are the probabilities along this path. So it is 1 by 3 into 1 by 4 into 1 by 4. So you can see here 1 by 3 into 1 by 4 into 1 by 4. Similarly, if you consider the sequence for the third state, let us check whether we are getting the same probability. Okay. For state 3, the state probability value is 1 by 3, right? And AB occurs here. So consider 1 by 3 into 1 by 4 into 1 by 4 for the sequence AB. So 1 by 3 into 1 by 4 into 1 by 4. So all these terms are for the sequence A, B only, but by considering state 1 as an initial state, by considering state 2 as an initial state, or by considering state 3 as an initial state. When you simplify, you will get it as 1 divided by 12. So we can easily state that for a symbol sequence AA, the probability of occurrence is nothing but 1 divided by 12. Okay. So it says that the probability of occurrence of the sequence AA as a message is nothing but 1 divided by 12. Sorry, not AA, it is for AB. Okay. Similarly, you can go ahead for calculating the probability of the sequence AA, probability of sequence AC, probability of sequence CA, CC, and other sequences also. Okay. So what you have to do is just make a table. In one column write down all the sequences, okay, and in another column write down the equivalent probabilities. Message here and then here probability of the corresponding message. Here I am considering message of length 2. Similarly, you can consider message of length 1 and write down the equivalent probability. When you consider message of length 1, the possible messages are only A, B and C. Okay, write down the corresponding probabilities. When you consider message of length 2, you have to consider all the possible combinations and write down the equivalent probabilities. So this table will help you in calculating the entropy. Okay, so in the next session we will see how to calculate the entropy based on the calculated probability values.